Hello there, math lovers, and welcome to my YouTube channel. Get ready to embark on an exciting adventure as we dive into the world of problem solving. In today's video, I am taking on a truly challenging task, an equation of order 11 that will put our skills to the test. But fear not, we'll tackle it step by step, unraveling its complexities with simplicity and clarity. So grab a cup of coffee, sit back, and join me on this fascinating journey of solving this extraordinary equation. Are you ready? So let's dive in. What do we have? As I said, we have an equation of order 11. And, well, how can we solve this? We know a formula for a quadratic equation, but here, obviously, we have to do something about this because there is no general formula to solve this problem. And so one way to attack this problem is to factorize this giant algebraic expression. But the question is, can we factorize it? But if you pay attention to the coefficients of different terms, you notice maybe an interesting thing. And that is the following, that if you pay attention here, you have 4x to the power of 11, and then here you have 4. These are the same, and then you have 4x10 and 4x. Again, the coefficients are the same, and then x9 minus 21, x2 minus 21, coefficients are the same. And pay attention that the sum of the powers of x, for example, in the first one, it's 11 and 0. In the second one is 10 and 1. In the third one is 9 and 2. The sum of the powers is always 11. And then the next one again is minus 21, and here minus 21. So here 17 and 17, and here you have 17 and 17. So there is something special about this equation. And these kind of equations are called reciprocal equations. So as you can see, the coefficients of different terms are equal in that the sum of the powers is always basically equal to the order of the equation. So there is generally a nice way to solve reciprocal equations. Let us first consider the most general form. And the most general form for an equation of order 11, or basically an odd number, is the following. So we have, let's say, x to the power of 2n plus 1 plus a 2n x to the power of 2n. Oh, well, let's just call that a1. And then plus a2 x to the power of 2n minus 1 all the way. So here we have a2 x to the power of 2 plus a1 x to the power of 1 plus 1 equals 0. Why was this a2? Because it's reciprocal. So the coefficient of x2 and x2n here, they have to be, x to the power of 2n minus 1, they have to be the same, because 2n minus 1 plus 2 equals 2n plus 1, which is basically the order of the equation. And here also, these coefficients are the same, and these coefficients are also the same. So that's why, because we're dealing with a reciprocal equation here. So what is so special about these equations in general when the order is odd? So here 2n plus 1 is odd. Okay, it's an odd number. The interesting thing about them is if you put x equals minus 1, then you get 0. In other words, x equals minus 1 is an answer. How do I know that? We can just do it. So if I put x minus 1, the first term is an odd power, so I get minus 1. Then the second term is basically a1 minus 1 to the power of an even number, which is a1. And this next one is minus a2. And all the way to a2 minus a1 plus 1. So this guy here cancels this guy, this guy cancels this guy, and this guy cancels this guy. And because here the total number of terms is basically 2n plus 2, it means that we have, in general, 2n plus 2 divided by 2, or n plus 1 pairs. So all the terms will cancel out each other, and as a result, this is 0, which means basically anytime I have a reciprocal equation with an odd order, such as 3, 5, 11, whatever, then x plus 1 is a factor, or in other words, x minus 1 is an answer. So that means here, by the way, you can also feel free to put x minus 1 in this equation, and you will see that x minus 1, as a matter of fact, is an answer. So it means this giant expression is divisible by x plus 1. So next, what I am going to do is to divide this expression by x plus 1 and try to find the result. So let's do that. So I have 4x11 plus 4x10. Well, I have to memorize that for a second. It's going to be a little bit difficult. So 4x11 plus 4x10. And here I have minus x9 minus x8. Okay. Then I have minus x9 minus x8. What else do I have? Then I have 5 times 17. Okay, let's just write that. 7. So guys, I could actually write the result, but I just wanted to do this operation so that you see, well, it's not really anything difficult. We can do it here. It's not really difficult. And then I have 2 minus 21 and 2, 4. So then I get here these guys plus 4x plus 4. So what we are going to do is we want to divide this by x plus 1. Okay? So let's see what we get. The first term is basically 4x10. And, you know, when we try to divide algebraic expression, then I have to multiply these guys here and change the signs. So then I get this, and then I have to sum these guys with this, and then here I get, well, these guys cancel each other. Then I get minus 21x9 and all these terms, which I have to unfortunately write it. I know it's a little bit tedious, but I have to do it. So here I have x4 minus 21x3 minus 21x2 plus 4x plus 4. As I said, I just do it so that you guys also, get familiar with this guy. I'm sure many of you know this. So minus 21x8 I get here, and then again I multiply, then I get plus 21x9 plus 21x8. You have to add them up, then this guy cancels this cancels this, then I get the rest, right? x6 plus x5 plus x4. And here I have minus 21x3 minus 21x2 plus 4x plus 4. And then I have to again divide this. Then I get plus 17x6 divided by x. And then here I get minus 17x7 minus 17x6. Again, add them. This cancels this cancels this. Then I have this one. 5 plus x4 minus 21x3 minus 21x2 plus 4x plus 4. And then I divide the next one, which is basically plus 17 divided by x. It's plus 17x4. And then I get first two terms, as usual, are cancelled. So here, this is cancelled, this is cancelled. Then I have this. Good. We're getting there soon. It's not really difficult. 2 more operations. And then here I get minus 21x2 So pay attention to the powers that jump 2 by 2. So 10, 8, 6, 4, and now I have 2. And then I get here 21x3 plus 21x2. And again, these are canceled. And then I have 4x4, and then the last term, which is basically I have 1, 4 here. And then here I get, remainder 0. Perfect. So I already proved that actually it is divisible by x plus 1. So let's call that giant expression S, the equation, and then at x equals x plus 1 times what we achieved here. So x10, x8. So for x10 minus 21, x8. What else do we have? We have plus 17x6, 17x4, plus 17x6, plus 17x4. And then we have also minus 21x2 plus 4. Perfect. Minus 21x2 plus 4. So we already have one answer, x minus 1. But let's now pay attention to the second term, second factor. Here, if you also notice, again, we have the same situation. So maybe I do it with a different color. So here, the power of x10 is 4, and this power of x0, x to the power of 0 is also 4. Here I have minus 21. I have here also minus 21. Sum of the powers are 10. Here I have 17. Here I have 17. Sum of the powers 6 plus 4, 10. So this is also a reciprocal equation, but the order is not odd. So in this case, for such situations, so whenever we have a reciprocal equation and the order is odd, we always have to divide it by x plus 1 so that we get another term, which is also happen to be, again, a reciprocal expression, and there the power is even. And now we do a beautiful change of variables as the following. I will show you. So let me change this color for a second. So before any change of variables, I need to first prepare this second expression. For that, I need to factorize x to the power of 5. How did I get x to the power of 5? Well, this power is obtained by dividing the order of this second expression by 2. As a matter of fact, the reason we needed the second expression to have an even order was exactly this, that we could divide it by 2 and we get an integer. So if I factorize x to the power of 5 from this expression, then I get x to the power of 5 times 4x to the power of 5 minus 21 x to the power of 3 plus 17x plus 17 over x minus 21 over x to the power of 3 plus 4 over x to the power of 5 equals 0. So x cannot obviously be 0, so just forget about this term here. And if I just a little bit order this expression, then I have x 4 times x to the power of 5 plus 1 over x to the power of 5 minus 21 x to the power of 3 plus 1 over x to the power of 3 plus 17 times x plus 1 over x. So in this new expression, you can clearly see that what can we take as a good change of variables. So just pay attention to these terms here. So if I take x plus 1 over x, let's say as sigma, there is a way that we can write these two expression as some function of sigma, but this is already also sigma. So let's just start with the simple one. So x to the power of 3 plus, so this is our change of variables, put it in the rectangle, and this can be written by the help of the cubic identity as x plus 1 over x to the power of 3 minus 3x2 over x minus 3 x times 1 over x2, but that is nothing but sigma to the power of 3 minus 3 times x plus over x, and that is precisely sigma, which gives me sigma 3 minus 3 sigma. Okay, so I got that. How about the second one? So x to the power of 5 plus 1 over x to the power of 5. Again, I'm going to use this identity here, which is basically a plus 1 to the power of 5. I'm sure you know how to expand this, so I just know it by memory, and I'm going to write it. So this is x plus 1 over x to the power of 5 minus 5x4, 1 over x minus 10x3, 1 over x2 minus 10 x2, 1 over x3 minus 5 x1 over x4. Okay, and then again, this can be written as sigma to the power of 5 minus 5 times x3 plus 1 over x3 minus 10 times x plus 1 over x. So we already found an equivalent for this guy here, which was here. So I'm just going to use that. So this is sigma 5 minus 5 times sigma 3 minus 3 sigma. Here I have minus 10 sigma. So if I just simplify this expression, I get sigma 5 minus 5 sigma 3 plus 15 minus 10, which is 5 sigma. So now I go back to the equation which I had, and that was this equation here. You remember that was the second term. So in this equation, I'm going to just replace these parentheses with what I found based on sigma. So I have 4 times the first one, which is basically 4 times this guy here, minus 5 sigma 3 plus 5 sigma. And then the second one is minus 21 and then 17. Okay, then I have minus 21 times sigma 3 minus 3 sigma and plus 17 sigma. This is equal to 0. So what do I get if I simplify this? I get 4 sigma 5 and then minus 41 sigma 3, and then I have 20 plus 63 plus 17 sigma equals 0. So I already know that actually sigma can be factorized, so sigma 0 is definitely one answer. So let's just factorize that. So I have sigma times 4 sigma 4 minus 41 sigma 2 plus 100. This is equal to 0. Even though this is an equation of order 4, but this is very similar to a quadratic equation if you just take sigma 2 as some new variable, and can easily be solved by the formula. So if I solve it by the formula for quadratic equation, then I get sigma 2 equals 41 plus minus square root of 41 squared minus 1600 divided by 8, and that is basically, this gives me the under square root is 81. Square root of 81 is basically 9, and that is 41 plus minus 9 over 8, which gives me 50 over 8 or 25 over 4, or basically 32 over 8 or just 4. And that means, so 1 sigma here, please pay attention that it was 0. So it means, generally speaking, sigma is one of these values. It's either 0, plus minus 2, and plus minus 5 over 2, if you just calculate the square root of that one. So going back to the equation that we had, the change of variables which we did, that was x plus 1 over x equals sigma. So I can find actually x based on sigma here. So this gives me this equation, x2 minus sigma x plus 1 equals 0. Or in other words, x equals sigma plus minus sigma squared minus 4 over 2. So, well, let's just substitute sigma with one of these values and find the x That's it. And just remember, we already had also 1x minus 1 when we did the factorization. So we're going to also take that into account. But let's just proceed with these values for sigma. So what if sigma equals 0, then I get basically x equals plus minus this guy over 2, and that gives me plus minus I, which is basically the imaginary number. So obviously for every sigma I am supposed to get 2 values for x. Please pay attention to that. So if I put sigma equals to 2, then I get x equals to 2 plus 0 plus minus 0 over 2, which is basically 1. But again, this is repetitive root. Okay, so as a matter of fact, I have 2x equal to 1 here because, yeah, the delta is 0, and as a matter of fact, I have repetitive roots. So if I put x sigma equal to minus 2, then I get x equal to minus 2 over 2, which is basically minus 1. Then I get 2 repetitive roots here. And if I put sigma equals to 5 over 2, then I get x equals, according to this formula, 5 over 2 plus minus, so that is 25 over 4 minus 16 over 4, which is basically 9 over 4. And that gives me 3 over 2 over 2 here. So it means that either it is 2 or it is 1 over 2. And if I put sigma equals minus 5 over 2, you can calculate it. It gives me basically minus 5 over 2 plus minus 3 over 2, which is over 2, which is basically either minus 2 or minus 1 over 2. So general, I could find these values for x as the root. So I'm going to write them for you here. So one was actually minus 1, and one was x equals to y, and x equals to minus y, and one was x equals to 1, x equals to 1, one was x equal to minus 1, x equals to minus 1, one was x equal to 2, x equals to 1 over 2, one was x equals minus 2, and x equals minus 1 over 2. So 1, 2, 3, 4, 5, and that is 5 times 2, 10, and here 11. So I have 11 roots for that equation of order 11, which is true, which is correct according to the fundamental theorem in algebra, which was basically the thesis from Carl Friedrich Gauss, the famous German mathematician, that every equation of order n has precisely n roots. So here I found 11 roots, and that was it, guys. And there you have it. We have reached the end of our mathematical expedition, successfully unraveling the complexities of this formidable equation of order 11. I hope you enjoyed this adventure as much as I did, and that it sparked your curiosity and love for mathematics. Remember, even the most challenging problems can be conquered with persistence, creativity, and a touch of mathematical brilliance. So stay inspired, keep exploring, and never shy away from the thrilling world of mathematical puzzles. Until next time, happy problem solving.